In today's video, I'm going to be showing you how to create a hoverboard. So what I've done is created a base plate project and published this place to Roblox. I'm now going to go into game settings, into world, and I'm going to set the realistic preset so that we change the gravity to 9.8 meters a second, and then press save. The next thing I'm going to do is go into workspace and I'm going to create a model. And then inside of this model, I'm going to create a vehicle seat. And I'm also going to create a part. And what I'm going to do is select the part, go into the model tab, click on this create button, select world, and I'm going to weld the part to the vehicle seat. The next thing I'm going to do is change the size of the part. So I'm going to go over to size and I'm going to set this to 2.5, 0.5, 7. And the next thing I want to do is increase the mass of this part. So if we scroll down, we should see it currently has a mass of 6. So if we select custom physical properties and go down into density and change this to the value of 10, we should see that the mass has now increased to 87. The next thing I'm going to do is select the vehicle seat and I'm going to change the size of the vehicle seat to 2.5, 1.5, and 2. And then I'm going to move this seat up so it's above the part. Then I'm going to make the seat invisible. So I'm going to set transparency to 1. And then I'm going to come down and set can collide to false and can query to false. But I'm going to leave can touch to true. And finally, I'm just going to move the entire model forward so it's not above the spawn plate, like so. Okay, so what I want to do now is when a character sits on this seat, I want to give them network ownership of this assembly. So inside of server script service, I'm going to create a script and I'm going to name the script network owner. Inside of this script, I'm going to create 3 functions. The first function is going to be called player added. The second function is going to be called character added. And the third function is going to be called seated. And now I'm going to connect these functions to events. So let's first connect the player added event. And then let's connect the character added event. And finally, let's connect the seated event. Now, inside of the seat function, what I'm going to do is use the active variable to detect if they're sitting down on the seat. And if they're not sitting down on the seat, we're just going to exit this function. So to do this, I'm going to say if active equals false, then return. Then the next thing I want to do is detect which seat they sat on. Now I only want this script to run for hoverboards, so what I'm going to do is change the name of the vehicle seat to hoverboard, and then I'm going to do a check here, say if seat.name is not equal to hoverboard, then return. And the next thing I want to do is get the player, and we can use the seat's occupancy property to detect which player sat down. So to do this, I'm going to say local player equals game.players get player from character seat.occupancy.parent. And then I'm going to check this player variable to make sure that it was set. So to do this, I'm going to say if player equals nil, then return. And finally, I'm going to give this player network ownership of the seat's assembly. So to do this, I'm going to say seat set network owner player. Okay, so now that we've finished the network owner script, let's now create a local script that's going to control the hoverboard once we receive network ownership. So inside of starter player and starter character scripts, I'm going to create a local script, and I'm going to name this script hoverboard. So the first thing I want to do in this script is detect when I sit on the hoverboard seat. So to do this, I'm going to first get the character, and then I'm going to wait for the humanoid, and then I'm going to create a function called seated, and then I'm going to connect the humanoid's seated event to the seated function. So the first thing I want to do is detect when we sit or get off of the hoverboard. So inside of the seated function, I'm going to say if active equals false, then this is what's going to happen when we get off of the hoverboard. And to check when we get on the hoverboard, what I'm going to do is say else if current seat.name equals hoverboard. So when we get on the hoverboard, I want to start a heartbeat loop. So to do this, I'm going to create a new function called loop, and then I'm going to get the run service. So at the top over here, let's get the run service. And finally, I want to store the connection to the heartbeat event. So I'm going to make a new variable called connection equals nil. And inside of here, when we sit on the hoverboard seat, I'm going to connect to the loop function. So I'm going to say connection equals run service, post simulation, connect loop. And when we get off of the seat, the first thing I'm going to do is check to make sure that the connection exists, because if the seat we sat on was not called hoverboard, this connection will not be set, so it will be still equal to nil. So over here, I'm going to say if connection equals nil, then return. Then I'm going to disconnect the connection. And then finally, I'm going to set the connection back to nil. The next thing I want to do is have access to this seat object inside of the loop, because this seat object has some properties, for instance, steer float and throttle float, that we're going to have to access inside of the loop. So to do this, what I'm going to do is at the top, I'm going to create a new variable called seat. And over here, before we start the loop connection, I'm going to set the seat variable. The next thing I want to do is create an attachment and place it inside of the seat. So at the top here, I'm going to create a new variable called attachment. And over here, after we've set the seat, I'm going to create an attachment and parent it to the seat. And when we get off of the seat, I'm going to destroy the attachment. So I'm going to say attachment destroy. The next thing I want to do is create a vector false. So at the top, just like before, I'm going to create a vector false variable. And over here, after we've created the attachment, I'm going to create the vector false object. And then I'm going to set the vector false's false to 0. And then I want to set vector false to apply at the center of mass. So to do this, I'm going to say vector false, apply center of mass equals true. And what this is going to do is going to ensure that even though the attachment is in the seat, instead of applying the false at the seat's position, we want to apply the false at the center of mass of the assembly's position. And then I'm going to set the vector forces attachment to the attachment we created above. And then I'm going to set the parent of the vector force to be the seat. And finally, when we get off of the seat, I want to destroy the vector force. The next thing I want to do is create a C-frame, and this C-frame is going to tell us what direction the hoverboard wants to face. So to do this, at the top, I'm going to say orientation equals nil. And over here, I'm going to set the orientation using the seat. So let me try to explain what we're doing inside of this from matrix constructor. So the first thing is the seat's C-frame may not be perfectly flat. For instance, it may be tilted on its side or tilted upside down or anything like that. But we want to create a C-frame that is perfectly upright. So what we're doing is we're creating a C-frame using from matrix, and the first value is the position of the C-frame. Now, we're going to be using align orientation, and align orientation doesn't care about the position of the C-frame, so we can just simply set the position to 0. The next thing the from matrix constructor requires us to input is the X direction and the Y direction. We can also provide a Z direction, but if we leave it empty, then the constructor will calculate the Z direction using the X and Y direction. Now for the Y direction, we're simply passing the Y axis of a vector 3, which is going to be 0, 1, 0. And that's going to say that we want the C-frame to point perfectly upwards. And in order to calculate the right vector, we can't just simply set the seat's right vector, because the seat right vector may be tilted and is not perfectly flat. So in order to calculate a perfectly flat right vector, what we can do is use the look vector and then cross it with the y-axis. So to visualize this, what we can do is imagine that the blue arrow is the look vector and the green arrow is the y-axis. And when we cross these together, it produces the red arrow, which is pointing to the right. Now, this y-axis is always going to point perfectly up. So this green arrow is never going to change. It's always going to point perfectly up. But the seat's look vector is not always going to be pointing forward. The seat may be pointing upwards, and we can see that even when the seat points upwards, it still gives us a flat right vector. And if the seat is looking downwards, it still gives us a flat right vector. So no matter which direction the seat is looking at, the right vector will always be flat. So now that we've created our orientation C-frame, let's create the align orientation instance. So at the top, I'm going to create a new variable called align orientation. And then once I've created the orientation C-frame, let's now create the orientation instance. So I'm going to set the mode to 1 attachment mode. I'm going to set the C-frame to the C-frame orientation that we created above. And I'm going to set the attachment to the attachment we created above. And finally, I'm going to set the parent to the seat. And I also want to destroy this align orientation when we get off of the seat. So I'm going to say align orientation, destroy. The next thing we're going to need is raycast perims, because inside of this loop, we're going to constantly be shooting a ray down to the ground in order to detect how far the floor is from the hoverboard. Now we want to use raycast perims to ensure that this ray does not collide with any of the parts inside of the hoverboard, and we also want to make sure it doesn't collide with the character. So to do this, at the very top, I'm going to create a new variable called raycast perims, and then over here under align orientation, I'm going to create the new raycast perims, and then I'm going to set the filter type to exclude, and then I'm going to set a table of all the instances I want to exclude. So I want to exclude the character, and I'm going to use the seat with the find first ancestor of class to find the hoverboard model. If we now test the game and look inside of Workspace and look inside of the model and look at the hoverboard seat, we can see that when I sit on the seat, and if we look inside of the seat, we can see the align orientation, the attachment, and the vector force. And when I get off of the seat, these instances get destroyed. Let's now add a custom animation when we sit on the seat. So to do this, what I'm going to do is go into my character, go into animations, and I'm going to steal the dance free animation. Now you can create your own animation, but just for this video, I'm going to take this animation from over here. I'm going to copy the animation and press stop, and then paste this animation into the hoverboard script. I'm then going to delete this weight, and I'm also going to remove the 1 from the name. Let's now load this animation onto the humanoid's animator to get the animation track. So over here, I'm going to say local animation track equals humanoid. I'm going to wait for the animator inside of the humanoid. Then I'm going to use the load animation, and I'm going to use the script wait for child animation, which is this animation over here. And then I'm going to set this animation track's priority. So to do this, I'm going to say animation track dot priority equals idle. Then when we get on the seat, I'm going to play the animation. And when we get off of the seat, I'm going to stop the animation. And if we test the game once again and sit on the seat, we can see it plays the dance animation, and when we jump off, it stops the dance animation. So let's now shoot our ray. So the first thing I'm going to do at the top over here is I'm going to create a new variable called ray offset. And I'm going to create a vector 3 with a offset of -8 on the y-axis. And this is going to tell us the world offset position from the position of the seat. So inside of this loop, let's now use the seat's position plus the offset to calculate the ray's target position. So I'm going to create a new variable called ray target equals, and I'm going to use the seat's position, and I'm going to add this offset onto the seat's position. And let's now create a raycast. So to do this, I'm going to say local result equals workspace raycast. And for the ray's origin, we're going to use the seat's position. And to calculate the direction of the ray, we're going to do the target position negative the seat position. And we're also going to pass in the raycast perims that we created down here. And let's now check the result. So I'm going to say if result equals nil, then this means that the ray did not collide with anything. So all I'm going to do is set the vector force's force to 0. And then I'm going to say else. So if we imagine that this green line is the ground and this orange cube is the hoverboard, and the target of the ray is -8 studs from the position of the seat. So let's draw the seat. And if we have -8 studs going down to the target position, let's imagine that the target position is over here. And when we shoot the ray down towards the target position, the ray is going to collide with the terrain, which is over here. Then what we're going to do is get the distance between the target position and the hit position. So this distance between these two dots is going to tell us the amount of force we want to apply to push the hoverboard upwards. So let's do it again, but this time with a hoverboard closer to the ground. So let's imagine there was a hoverboard over here. And here is the seat. And we have a ray that goes -8 studs. And here is the target position of the ray. And this is the collision position of the ray. And if we measure the magnitude between these two positions, we should get a greater force when the hoverboard is closer to the ground versus when the hoverboard is higher above the ground. So let's now get the magnitude between the target position and the results position. So to do this, I'm going to say magnitude equals result.position negative the ray target position, and we're going to get the magnitude. Now, to adjust how powerful this magnitude variable is going to be, we can create a multiplier to multiply this magnitude variable with, and I'm going to call this thrust. So over here, I'm going to create a new variable called thrust, and I'm going to set it to 2000. Then I'm going to set the vector force using the magnitude multiplied by the thrust. So to do this, I'm going to say vector force.force equals vector3.new, and I'm going to use the magnitude multiplied by the thrust. So let's now test the game and see what happens. So once I sit on the seat, we can see that once the ray collides with the floor, it pushes the hoverboard upwards, and we constantly go up and down, like so. So that we can visualize what the ray is doing, let's create a part and position it at the ray's hit position. So to do this, over here, I'm going to create a new part called ray part, and I'm going to anchor this part. I'm going to set can collide to false, can query to false, can touch to false. I'm going to set the shape to a ball. I'm going to set the size to 1, and I'm going to set the parent to workspace. And down here, if the result is equal to nil, which means the ray never collided with anything, I'm going to set the part's color to green, and then I'm going to position the part at the target position. But if the ray does collide with something, what I'm going to do is set the part's color to red and set the position to the results position. And if we now test the game again, we should see the ray, and when the ray goes down by 8 studs, and if it does not collide with anything, the part will be green, and when the ray does collide with something, the part will be red. Let's now work on the align orientation. Vector force is in object space. So when we apply the thrust to the hoverboard, we're applying it relative to the rotation of the hoverboard. So what that means is, if we imagine that this is the hoverboard and it's flat, then when we apply the force, it's going to apply the force upwards like this. But if we imagine that the hoverboard was tilted forward, because the vector force is in object space, instead of applying the force upwards like this, it's going to apply the upwards force like this, which is going to allow us to move the hoverboard forward. So in order to tilt the hoverboard, what I'm going to do is I'm going to copy the align orientation.cframe equals orientation into the loop. And what I want to do now is multiply this orientation C-frame with a tilt C-frame. And in order to create the tilt C-frame, I'm going to use the hoverboard's seats, steer float, and throttle float. But I want to multiply this by an angle, and this needs to be in radii. And we could create a variable at the top here to determine how much to tilt the hoverboard. Or another option is we could just use this torque property. And because it's in radii, I'm going to set this to 0.7. And now, above when we set the C-frame, what I'm going to do is say local tilt orientation equals C-frame from orientation. Then I'm going to say negative throttle float multiplied by torque, which is this 0.7, which we set over here. For the y-axis, we're just going to use 0. And for the z-axis, we're going to use negative steer float multiplied by torque. And then I'm going to multiply this tilt C-frame onto the orientation C-frame. And if we now test the game, I should be able to use the W key to tilt forward, and the S key to tilt backwards, and the A key to tilt to the left, and the D key to tilt to the right. One thing you may have noticed is because we're setting the vector force to 0 when the ray does not collide with anything, if we try to tilt while the part is green, it doesn't have any effect on the direction that the hoverboard wants to go. But if we tilt while it's red, it does have an effect on the direction the hoverboard will go. So what we can do is have a minimum amount of thrust even when the ray does not collide with anything. So in order to add minimum thrust, above the thrust variable, I'm going to create a brand new variable called minimum thrust, and I'm going to set it to 600. Then, instead of setting the vector force to 0 when the ray cast does not collide with anything, I'm going to replace this and I'm going to say vector3.new, and I'm going to set it to the minimum thrust. And then I'm also going to add the minimum thrust to when it does collide. So over here, I'm going to say minimum thrust plus magnitude times thrust. So if we now test again with minimum thrust, what we should notice is that the hoverboard feels a little bit more floaty because it's still pushing upwards even when the ray is in the green. And if we try to turn, we have a very small amount of control over the hoverboard even while in the air. And if I set minimum thrust to 3000, now we should notice that the board becomes even more floaty. And I have a lot more control while in the air. We currently have two problems that can be solved with a single solution. So the first problem is our hoverboard keeps bouncing up and down, up and down. Now you may first be inclined to think that we need a PID controller to solve this problem, but I'm going to show you a different way of solving this problem. The next problem we have is because our ray only shoots downwards, the ray is unable to detect changes in height in the terrain in front of us if we're flying forward at high speed. So if I start flying forward, our hoverboard will collide with this wedge in front of us. So if I start going forward, we can see I collide with the wedge. So to fix these two problems, all I'm going to do is add the seat's velocity onto the ray's target position. So over here, I'm just going to simply say plus seat's assembly linear velocity. Now I want to scale this value down because it's going to be too high. So over here, under ray offset, I'm going to create a new variable called ray velocity, and I'm going to set it to 0.2. And I'm going to simply multiply this assembly linear velocity with this ray velocity. So over here, I'm going to say multiplied by ray velocity. And if we test the game again, and I go on the hoverboard, we should see that the hoverboard no longer bounces up and down. And if I go to the right, we can see the ray starts going to the right. And if I go to the left, the ray starts going to the left. And because now the ray goes forward and back based on the velocity of the hoverboard, it should be able to predict the future better because it's now testing what's in front of the hoverboard. You may be wondering, how did we stop the hoverboard from bouncing by simply adding the velocity to the ray target position? So let's imagine that we have two hoverboards here, and here we can see the 8 studs of offset, which we have set up here. And on top of this offset, we're adding the velocity of the hoverboard. So let's assume that this hoverboard on the left side is falling downwards, while the hoverboard on the right side is being pushed upwards. Now this hoverboard on the left side, because it's going downwards, we add this downwards vector onto the end of the target position. So this is going to extend the target position, which is going to extend the length of the ray. And on this hoverboard on the right side, we're going to add a upwards vector because the hoverboard is going upwards. So it's going to shorten the length of the array. So now the new target position for this hoverboard on the left is going to be down here, while the new target position for the hoverboard on the right is going to be up here. And then we're going to get the magnitude. So if you remember, we got the magnitude over here. And this magnitude is going to be larger than this magnitude on this side. So from this, we can see that a hoverboard which is falling down towards the ground will have a stronger force pushing it upwards, while a hoverboard moving away from the ground will have a weaker force pushing it upwards. And this is going to cause the dampening effect. Let's now add the ability to turn the hoverboard. So if we select the hoverboard seat and scroll all the way down, we can see here is a variable called turn speed, and currently this does nothing, but I'm going to use this value to adjust how fast the hoverboard turns. So this is going to be radii per second. So I want the hoverboard to rotate at a speed of 5 radii per second. And to use this variable now, what I'm going to do over here is I'm going to say orientation multiplied equals C-frame from orientation, and I'm going to use the steer float, and I'm going to multiply it by the turn speed. And so that the frame rate doesn't affect the turn speed, I'm going to multiply it by delta time, which will cause the hoverboard to rotate 5 radii every second. And if we now test again, if I press the A and D keys, I can now rotate the hoverboard. Let's now add drag to our hoverboard. So if I start flying forward and stop flying forward, you'll notice that the hoverboard never slows down and continues at 37 studs per second. So in order to have drag, what we need to do is add the negative of the seat's velocity onto the vector force. But we have a problem. This velocity is in world space, while the vector force is in object space. One option we have is to create a separate vector force, which is set to world space, and then we can use the velocity directly. Or another option we have is to convert this velocity into object space. So to convert it to object space, what I'm going to do is say local velocity equals seat.cframe, and I'm going to use the vector to object space, and I'm going to pass in the velocity vector, and that's going to convert it into a object space vector. And what I'm going to do now is add a new variable called drag and set it to 0.02, and then I'm going to use the velocity and drag to adjust the vector force. So to do this, I'm going to say if velocity.magnitude is greater than 0, then I'm going to say vector force.force negative equals, and I'm going to use the unit of the velocity, and I'm going to multiply the unit by the drag variable and by the velocity squared. And if we now fly forward and stop, we should see that our speed slowly slows down because of the drag. And if we wanted to make drag more stronger, all we need to do is increase this drag variable. So for instance, if I change this to a value of 2, and now we should see that drag pushes me back a lot stronger. So we can see that I can no longer go faster than 39 studs per second. And as soon as I stop pressing W, we can see that my speed quickly reduces. The next thing I want to add is a counter tilt. So what this is going to do is going to be just like tilt, but instead of using the throttle float and steer float to tilt, we're going to calculate the counter tilt based on the velocity of the seat. So if the seat is going very quickly forward, it's going to tilt backwards to counter the velocity. So to add counter tilt, underneath drag, I'm going to create a brand new variable called counter, and I'm going to set it to 0.004. The next thing I'm going to do is calculate how much we need to tilt the C-frame based on the velocity. So underneath the tilt orientation C-frame, I'm going to create a new variable called counter x, and I'm going to use the linear velocity on the z-axis multiplied by the counter variable we created, and I'm going to clamp this rotation by the torque value that we set inside of the seat. You may be wondering, why are we using the z-axis for the velocity but the x-axis for the rotation? So if we imagine that the hoverboard is going through the z-axis, in order to counter this, we must rotate on the x-axis. So we're going to rotate around on the x-axis like so to counter the z-axis. And let's now do the same, but for the z counter. So I'm going to say local counter z equals math clamp. And this time, instead of using the z-axis, we're going to use the x-axis for the velocity. And we're going to use the counter variable just like before. And we're going to clamp it to negative torque and positive torque. So let's now use these two counter variables to calculate our counter C-frame. So to do this, I'm going to say local counter orientation equals C-frame from orientation. And I'm going to use the X and Z counter to calculate the C-frame. And let's now apply this counter orientation C-frame onto this align orientation C-frame. But the order we apply it in is very important. We must first apply the counter C-frame. And the reason for this is because assembly velocity is in world space, and we want to apply this tilt before we have orientated the hoverboard. Once we've applied the world space tilt, then we're going to orientate the hoverboard, and then we're going to apply the tilt that is done with the WASD keys. So that we can see this tilt work even better, I'm going to disable drag by setting drag to 0. So what we should notice now is, even though we have disabled drag, the counter tilt is going to work a lot like drag. So let's go on the hoverboard, and if I start flying forward, and if I stop flying forward, we should see that I tilt backwards to counter the velocity, and I'm now reducing in speed. So counter tilt works a lot like drag. And if I tilt forward and then quickly spin to the left, we can see that my hoverboard tilts to the left to counter my velocity that's going to the right. And if I increase the counter variable from 0.004 to 0.02, we should notice it works just like increasing drag. So if I start flying forward, we can see as I increase my velocity, it starts countering in tilting backwards, and it prevents me from going over 35 studs a second. And when I stop, it brings me to a stop a lot quicker. And if I want to turn left and right, it prevents my hoverboard from drifting. So a lower counter value will feel more drifty, while a higher counter value will feel less drifty. So while drag and counter have the exact same effect, I like to have a mixture of both. So I like to have my drag set to 0.008, and I like my counter to be set to 0.004. And now that we've finished our hoverboard script and we're happy with how our hoverboard is flying, we can now delete the ray part. So I'm going to delete the ray part here, and I'm also going to delete this part here. And now we have a completed hoverboard script. Thank you for watching my video, and if you have any questions, feel free to leave a comment down below.